Guten Tag, Damen und Herren. Es ist eine Freude, hier zu sein. Ich liebe diese Stadt. Ich liebe Currywurst und über alles deutsches Bier. Ich habe ein bisschen Deutsch gelernt in Brasilien, aber ich denke, es ist nicht genug für diese Präsentation zu machen. So let's change to English. Good afternoon again. My name is Wardner Maia. I'm an electronic engineer, and I've been working as an ISP in Brazil for many years, since the very beginning of the commercial internet in our country in 1995. Our company is still a ISP using fiber and radio. And we are also MikroTik training partners and MikroTik distributors in Brazil. There are some other presentations in the last European MOOCs, and the last one was about IoT, Internet of Things, IPv6, and the challenge for Internet security. And today, I would like to talk about a subject that is not new, is about the transition of IPv4 to IPv6, but I think I would like to bring some thoughts about this moment of changing in the internet. So, the specialists in human behavior say that we have two types of mindsets: the scarcity and the abundance. The scarcity mindset, the vision of the scarcity mindset, is that everything is needed for the future survival and progress is getting scarce or running out. And this is our IPv4 world, because every day we have to fight with the scarcity of IPv4. And scarcity leaves us feeling overwhelmed, depressed, and paralyzed. On the other hand, the abundance mindset says that everything important is getting bigger and better as a result of capabilities that make things faster, easier, and cheaper. And in the new moment of the internet, where we have, in the last 5 years, we have a lot of devices, we have a lot of smart devices, a lot of IoT devices. This is our IPv6 world. We need IPv6 to continue the internet growing. And abundance makes us feel excited, motivated, and ready for action. We will divide in 4 parts. This presentation is a short presentation. The first part is about the current status of IPv4 exhaustion in the IPv6. Then the issues related to shared address solutions and IPv4 scarcity. The CGNAT implementation using MikroTik OS with low cost and good performance. And the best practice for IPv6 deployment in a small, medium ISP access network. So this map, we can see the stock of IPv4 all over the world. The world is divided in 5 regions in terms of IP addresses management. And in all the regions, we have less than 1/8 per region. This is the graph of the decrease of IPv4 stock starting in 2013, and now we are in this moment here. If we note with some detail, there are some stock of IPv4 in many countries because of the exhaustion policies adopted by, this is RIPE, your region, this is our region, and then we have a smoother curve for decrease the IPv4. Whenever we talk about IPv4 exhaustion, IPv4 scarcity, some people ask about the legacy space, the reserved space. There is much IPv4 space that are not being used nowadays. And at the very beginning of the internet, a lot of blocks have been assigned for institutions like US government, like some universities, and most blocks of them will never be used. And every day we know some news in the newspapers, we know some news about some companies selling millions, like MIT last year, selling 8 million of IPv4 addresses. We have also a lot of space, a lot of reserved space. IETF reserves space for multicast, for future use, for loopback, a lot of space, like 35/8 space reserved. And the question that came on mind is if recovering such space could be a solution. Could the RIRs take back the space and distribute, and will be a solution? If we look to the IoT forecasts, Gartner Group forecasts that in 2020 we will have 20 billion of connected devices, of IoT devices. I3E Spectrum forecasts that we will have 50 billion of connected devices. IPv4 space is only 44.3 billion addresses. So IPv4 is not the solution. The only solution is IPv6. And how is the IPv6 adoption status in the world? This map is IPv6 adoptions as seen by EPNIC. EPNIC has some method for measure distributing in some sensors around the world, and every time an end user goes to a website where a sensor exists, it will test if the user has IPv4, IPv6, or both, and this is a dynamic map. There you can access the IPv6 adoptions in the final customer. I'm not talking about adoption of content providers, about the final customer. And you can see that India is the leader with more than 60% of IPv6 adoptions. Germany and US more than 40%. In Brazil, we have a not so good number, but for me, it's a good number because it's 25% this year, and 3 years ago, we were below 5% of IPv6 adoption. So IPv6 is a reality. And this is the progression of the curve of adoption of IPv6, as seen by Google. Medium, 22% of final devices connected. And note that IPv6 has more than 20 years of existence, but only this curve only take off here in 2012, coincidentally, when the EPNIC stock of IPv4 exhausts. So, we will have IPv4 at least 2020, maybe 2021. All the stock, the technical stock, will exhaust. So, and we have to survive at this moment to the transition because we need to provide the service with IPv6, but we can still provide the service, continue to serve the IPv4 addresses. And there are some issues related to IPv4 sharing. The shared address solutions are stated in the slide, but we will focus in CGNAT, carrier grade NAT, or LS NAT, large scale NAT. The first issue is about traceability, because when you do NAT, the users behind that NAT will not be traceable. And there are some concerns about a large-scale NAT. When you do the traditional NAT in a user or in a company, you know that is that company using. But when you do in your structure, you have to do more logging to guarantee the traceability of the users. The technical community has some arguments. The RFC 6302 has recommendations for internet-facing servers. The internet-facing servers have to should log the port number. Besides the IP address and timestamp, the internet-facing servers had to log the port number of that user. In the side of the ISP should, for each user, log the IP, the public IP, and the port number that user was using. Okay, but how big would be the ISP logs if we log without control? We log the activity. How big could be that log? Of course, it will be very space-consuming, and for this reason, this RFC recommends a pre-allocating of group of ports for users. So we do not need to log, but we need to apply a schema, a distribution of the number of the ports fixed per user. And the strategy is to give for subscriber 1, the private IP 1, subscriber 2, private IP 2. All these subscribers will share one public IP, but with only one public IP port range. Which ports can be used for this schema? IANA ports is divided in three ranges, well-known ports, registered and dynamic. And well-known, of course, we cannot use because is where our services like web, FTP, etc. Run, and these ports we cannot use. And the doubt is about the registered ports. Fortunately, this RFC has a recommendation that there is no problem to use the registered ports for CGNAT. So we have in total 64,000 ports for CGNAT. And how many ports per user? This is a difficult question to answer with few words because it depends on a lot of things. We have to consider that each application has a group of ports. Usually some applications open, like Google Maps, open 30 or 40 ports at the same time. And there is also the TCP time wait. That's a time that a port is reserved even after the connection finished. And there are problems also that operating system has to make the port randomization because of security problems, and all this behavior of the connections, we have to reserve a bigger amount of ports than the applications were using. Of course, it depends if you are providing service in a hotspot for cell phones, for example, you can use a small amount of ports. But if you are providing to residential broadband, fixed broadband, where several devices will share, that you have to provide more ports. So, to plan the IPv4 in times of scarce resources. Suppose a situation where one hypothetical ISP wants to target of 25,000 customers, 25,000 customers in 3 years. But currently, this ISP has only 1,000 IP. Of course, he has to do CGNAT with a sharing ratio of 1 to 25. And the number of ports per customer should be 2,580 ports per user. So we can divide these ports. This range of ports is for subscriber 1, 2, until subscriber 25,000. And how to deploy this? You can buy an expensive box. There are some dedicated hardware to do CGNAT, or you can follow some RFCs and deploy with MikroTik RouterOS. And I assure you that you will have good results using RouterOS for this purpose. So, how is the implementation in RouterOS? Note that the reserved space for CGNAT is 164.00/10, and the first approach is to share this among users and share the users with the public IP. The first approach in MikroTik was in that link, in MikroTik Wiki, and is that script to do this. But with this implementation, we'll have one role for one user for TCP, one role for UDP, and one role for other protocols without orientation to ports. So this is the private IP address, and this is the public IP address, and this is the range, the port range. I do 3 roles per user. The next user will be 165, and the other will keep as is. So, with this implementation, we'll have a sharing ratio of 1 to 25 or 25 to 1. We have to have 75,000 rows. That is very, very hard to process such number of rows. So, fortunately, RouterOS provides another features to make these things better. NetMap. NetMap was initially ported in Linux. The old guys maybe will remember there was a patch in the IP tables, Patch-O-Matic, with several features. One of these features was NetMap. That was ported to RouterOS 2. And how NetMap works? NetMap works doing a translation of a network to other network. Suppose I want to translate 1100/16 to 2200/16. Only the network part of the network will be translated. So the IP 11xy will be translated to 22xy. And with this feature, we can implement our NAT, or CGNAT, using NetMap, translating the network 164.66 to an IP, another IP, public IP. So, in this case, the subscribers will receive the first subscriber 164, and this range of port, 165, this range of port. The typical NetMap roles will be source NAT, TCP, and the IP, the public IP address, action, net map. The other for UDP, and another for other protocols is missing one slide here. So, in total, we will have only, if we have 1 to n sharing ratio, we will have n rows for TCP, n rows for UDP, and one row for non-port-oriented protocols. So, our hypothetical ISP, instead of 75,000 rows, can do the same thing with 51 rows. Here is an example of implementation in RouterOS using a sharing ratio of 1 to 7. This is the same we use in our trainings to show the things in a didactical way. So we divide in groups of ports of 10,000 ports per user. Only the first and the last user will receive less ports than 10,000. And the schema is to give to subscriber 1 the IP 100, 100, the first range. 100, 101, the second range. And with this implementation, it's very easy to answer if we receive some authority requirement about who was using that IP and port. With this IP and this port, I know that this is range 0. So the IP internal will be 100, 100. This will be range 5, 100, 105. This will be 101, 100, 101. So there's no need to log anything, just to keep the table you did the distribution. So about net map rows, this implementation is 7 rows for TCP, 7 rows for UDP, and the final rules for other protocols. When implementing this technique in our network, you notice one problem that can happen if we implement that we form static loops. The reason is because, in fact, the public IP address is not configured in an interface. The public IP address is published by our BGP, and the border router has a route to the concentrator. So, in the concentrator, we do not have this IP. We have only the CGNAT, the net map role. And then, when a packet is generated inside the network, it's okay, because the connection tracking will track the connection and guarantee the both way of the packet. But if one packet is generated on the internet and generated destined to one IP, an internal IP, the border router will route to the concentrator, and the concentrator will have no route to that IP, and will send back to the border router. And the border router send back to the concentrator, and we make a loop until the TTL expires. So this is very bad because we have undesired traffic, and we can amplify attacks. If we receive attacks on one IP, we are a factor of amplification, internal factor amplification. The solution for this is very, very simple. There are very possible solutions. We can create a destination rule pointed to a public IP address in the concentrator, or to a black hole address in the concentrator. We can configure all the public address in loopback interfaces. I don't like the solution, but it was suggested by, is this possible, okay? Or we simply can black hole the route for the entire public network and the concentrator. And this implementation is very easy and can be applied without any change in the topology. Some guys would like to work with a central concentrator, with only one concentrator. And okay, he will put the roles in this concentrator. The ones that are working with distributed concentrators per point of presence have to do the net map roles on the distributed concentrators. So you do not need to change anything in our topology to implement the CGNAT. And finally, about CGNAT, one problem is about the port forwarding. Usually, we have the problem of port forwarding using the natural net, the common net, one level of net, and we have to go to the CPE of the user CPE, make a port forwarding, a destination NAT in the user CPE. So, when you use CGNAT, you need another level of NAT inside the concentrator. So, to simplify the work of the people of the help desk, the support people, we can create some pre-configured roles forecasting some ports the user will ask us. Like, for example, we have two users, one user 164, another user 165, and both users are sharing the same public IP addresses. So both addresses ask to forward to port 80. What happened in this case is that we have pre-configured roles in the CGNAT, and the only thing that the help desk should inform is that to access the device, the user has to, when he was out of the place, out of the house, he will use this port, and the internal device will be with this IP. All these things we can automate with scripts, and it are pre-configured in the concentrators. So, finally, let's talk a little bit about IPv6. IPv6, you know, the biggest difference of IPv6 and IPv4 is the size of the space. We have in IPv4 40.3, approximately 40.3 billion, and IPv6 an unpronounceable number here. Okay. And the first thing when working with ISPs is the planning of the distribution. Most ISPs are a little bit concerned about starting to plan the ISP, the IPv6 distribution, because of the problems we had with IPv4. And a lot of people think in IPv6 when as IPv6 was equal to IPv4, and it's very different. So, to make a good address plan, we have to have some things in mind. First of all, the minimum allocation for ISPs in all RIRs in the world is /32. The small ISP in the world will have a /32. The longer prefix allowed in BGP is a /48. And the minimum allocation that allow stateless auto-configuration to work is a /64. Stateless auto-configuration is a good thing for IPv6 because, of course, inside the home, the devices will connect to the internet, will configure itself without any configuration, and will start to use the IPv6. So we have to provide at least a /64. But the current recommended allocation, according to this RFC here, is a /56 for residential customers and a /48 for business customer. Here we have 256 subnets. That's a quite big number for a residential customer. The customer can be 200 subnets inside the house. So that's the way we start to plan our distribution when we were surprised by a recommendation of the RIPE with this best current operational practice operators, BCOP, this document in October last year. And the BCOP is recommended allocation of a /8 per user, even for domestic users, all the people with /8. This sounds a little bit crazy, because why should I allocate an IP address to a customer that could have 65,000 subnets inside a home? Maybe IP is trying to exhaust IPv6 and we work with another protocol in the future. So, in fact, seeing the history, this recommendation is not new. In 2001, the recommendation was the use of a /48 even for domestic residential subscribers, and even for on-demand connections like dial-up, I think. So the recommendation in 2001 was changed 10 years later by this other RFC. But if you look to the RFC, you don't find much technical reasons to change this recommendation. The reason is like the recommendation was criticized for being wasteful. It's hard to argue that home sites will make the use of 65,000 subnets, and nothing more technical. So, the RIPE documents has some points, lists some points, some technical points recommending, but the most attractive, in my opinion, was the simplified addressing plan for your customers, for your whole network. The BCOP doesn't condemn the RFC, but points recommendation that if you want to give /56 for commercial reasons, because I think it's the commercial reason to differentiate domestic and enterprise user, if you want to give, reserve the full range of 48 for each customer. And the question is, okay, if I follow this recommendation, will my block enough big to give /48 for all my customers? If you have a /32, how many customers could we provide service if we give a /56 and about /48? The answer is here. If we provide /56, we can provide service to 16 million of subscribers. One small ISP that has only a /32. And about /48, we can provide service for 65,000 customers. Okay, someone can argue that you waste space waste space when you are doing the infrastructure, subnets, etc. Okay, but even if you have 30% of space wasted, and you can provide service for 40,000 customers. In my country, we have 7,000 ISPs, and I don't know 20 that has more than 40,000 customers, all below this. So, maybe the B Corp cannot give us a good reason to give a /48 for our customer. But we cannot give a good reason for not to give, for not allocate this. And if you do this allocation, there will other benefits. One of the benefits could be in terms of security. This is not point mentioned in the B Corp, but thinking about the subject and thinking about how today the DDoS techniques work. Let's see in IPv4. Suppose we are this ISP and we have an upstream provider that's providing service, and this upstream provider has a policy that with this community, if I make an announcement with this community for a /32, he'll put this /32 in black hole, and the communication with the /32 is lost, but the channel overflow will stop. I will avoid the DDoS attack. For IPv6 is the same, but in this case here, I need that my upstream provider has the community policy. And it should work for the technique to be effective. So, in the case I'm announcing, I'm giving /48 for my customers, I simply split my, and my upstream provider does not provide such type of community, I can simply do not announce the attached block. I can black hole without announcing that /48. In the case of other ISPs that have a contract with a mitigation provider, suppose this is IS has a contract with this mitigation provider. This mitigation provider usually is a big guy with a lot of bandwidth, a lot of hardware and software to support big attacks and to clean the traffic and to send you via one tunnel to send you the traffic clean. So, how it works? When 1/32 is attacked here, this IS will announce the whole /24, because in IPv4 we cannot announce nothing less than /24, and this mitigation provider will announce to the internet, you start to receive the traffic and filter the traffic and send via one tunnel the clean traffic. This technique is okay, it works, but the customer, all the customers belonging to the /24 block will suffer delay because of this tunnel. So, the difference, if we give /48 for our customers, we simply announce this /48 for the mitigation provider. The mitigation provider announces, and only one customer will suffer the delay. So, for me, this is a good reason, two good reasons to implement /48. You simplify your planning and for security reasons. So back to the planning. The anatomy of IPv6 is this. Here is 4 bits, is an hexadecimal, 8 bits, and 128 bits. So, considering this anatomy, it's interesting to plan the distribution with hops of 4 bits, not bytes, bits. 4 bits. This will turn our distribution cleaner and easier to understand. It could avoid future mistakes. How it works? Suppose I have a /32 block. I split in 16/36, for example, for provide service in 16 cities, different cities, and each /36 I split in /40, and I can in each city have 16 POPs, and in each POP I can have 256 users /48 per POP, or 4,048 per city. Of course, this can be adjustable because we can route 2 or more blocks for 1 POP and for a bigger POP, or 2 blocks /36 for a bigger city. This is adjustable. But in fact, this will simplify your address planning a lot. Another hint about address planning is to reserve part of our blocks to infrastructure for loopback interfaces, for point-to-point internal interfaces, etc. And we can divide the blocks reserved and blocks that IPs that must be announced. I mean, routers that have external connections with other ASs, but we have parts of our network that may be announced. I cannot announce it, like point-to-point links. This is interesting because I simply cannot put in the BGP the IPs and provide some protection, less exposition of my network. So, continuing with the BCOP 690, about fixed or dynamic addresses. There are some problems related to dynamic address. First one, logs. Of course, if the IP is dynamic, I have to provide some way to collect the logs. There's no problem, but issues related to internal services. If the users want to run some service like a web server, etc. And problems related to power outage. This is the biggest problem in IPv6 implementation in the end users. The problem is because the CPE will get an IP address from the concentrator, and the CPE will provide the router advertisement for the internal devices. So all the internal devices will be configured for that router advertisement, and suddenly there's a power outage. The CPE do not inform to the devices to clean that IP address, but the CPE will get another IP address from the concentrator, and then will make another router advertisement with another IP address. And most of the operating systems will configure a second IPv6 address and a third IPv6 address. And if the things are not going well, the user goes and boot the CP, and another address came up. So this is the problem related to dynamic IP addresses, IPv6 addresses in IPv6. And most of people do not notice this problem because most of ISPs are providing double stack. And if the IPv6 doesn't work, the operating system, the application changed to IPv4. Then you are not really using IPv6, but using IPv4 in these cases of failure. So this is the reason that the BCOP recommends to use fixed, permanent addresses. Well, PPP and DHCPv6 support. You know that we can use the DHCPv6 in final customers, like in the SXT, for example, to get the IPv6. Here usually is the PPPoE interface, and we request the prefix, and this pool will be generated internally to give the addresses for address SLAC. And the IPv6 pool, we can define a pool and a prefix for splitting the pool. And the dynamic allocation can be done simply if we configure the pool, a bigger pool, and a prefix length to distribute to the customers. And there's a problem with traceability that we can solve with MikroTik, with scripting on logon. I can send to syslog, and we can solve this problem. So, but the main problem is about fixed delegation by radius. How do I do a fixed delegation? I want to give a permanent address to my customers and distribute it via radius. There is a thread in MikroTik forum asking for this delegated IPv6 prefix, because RouterOS support prefix delegation. However, it's not possible to direct get from the radius server via such prefix. But there is a way to circumvent this limitation. RouterOS supports the attribute MikroTik delegate IPv6 pool, but this is one string. But I can associate this string with an user. And in radius, we will have the user credentials and the name, the string. And all I have to have is in the concentrator, I have to have a pool with the same name of this string. And then the user gets the string, the pool is configured inside the MikroTik, and the user will get that fixed pool every time he logs in. So the conclusion is that it's possible to implement both things, to do implementation of CGNAT using RouterOS and to implement in the correct way the IPv6. And some things can sound a little bit obvious, but it's important to mention that the CGNAT techniques are very helpful in this phase, but CGNAT is not sustainable in the long term. We need to remember that the number of ports is limited. So, in one moment, CGNAT will not work, will break everything. So, IPv6 is totally different of IPv4. And we should not use the same concepts. We should not use the same paradigms. IPv6 is abundance, and you have to use, do not be afraid of giving /48 for your customers. There are enough IPv6. And for the ones that didn't start the IPv6 implementation, don't wait the time limit. There is no time limit. Time limit has gone. So, as references, we have the BCOP that I mentioned. I recommend this document, and also for the ones that are implementing IPv6, this is a good BCOP about IPv6 troubleshooting for residential ISP help desks. There's a good guide to your help desk to solve some common problems related to IPv6 deployment. So, vielen Dank. That's all. I'm ready for it.
Thank you very much. This is our last presentation today.